talking about it. Very popular. You also got only about 64 bytes of RAM, but you also have some EEPROM, which is non-volatile. You know, once you turn the power off, it can actually remember some settings. If it was wanting to map out its environment, like it's this many timer ticks from this wall to this wall, or this many units over here, or I've bumped into the wall this many times in the course of my lifetime, you could actually remember some of that stuff. Up to 6 general purpose I/O pins, a counter timer peripheral that has pulse width modulation, which we need for the servo motors, 4-channel analog digital converter, and an external interrupt controller, where you can have it stop running the program that you're running and have it go to an exception handler and then come back when the foreground program doesn't even need to know that happened. You don't have to sit there and wait for things. All that in 8-pin chip for about $1. Now, the thing is, there's better chips available now that do a whole lot more for even less. But, you know, past a certain point, you know, it just becomes ridiculous how much horsepower you can get for, you know, $5.
Yeah.
You know, if you're willing to go ahead and spend $7 or $8, you're in tall cotton. You know, there's all kinds of good stuff.
Like the Mega 328.
Well, yes, the Mega 320 is only about $3. Which is what's on the Arduino.
Discovery, probably.
I'm sorry?
You're talking about things like the Discovery, probably.
Yes, there's some 32-bit processors that are out. There's very low cost, run 50 megahertz, have 20 or 30 I/O lines, you know, a dozen timers, just nuts. You know,
Hundreds of megabytes. I mean, hundreds of kbytes rather.
Yes, well, anywhere from 60 to 512 K or 1 meg of flash. I mean, just insane amounts of.
Or the propeller with like 8 cogs on it.
Yes, multi-processors for aren't they like around $10 now?
About.
Yeah, it's just you can get a lot of computing power for very little money, but we're talking the very lowest end,
Entry
product.
level.
Yes, entry level, because and it's something you can actually comprehend. I mean, you can know everything there is to know about this chip, given a short amount of time, because there is a finite amount of things that it contains. So we're going to talk about the input and output pins. Other than power and ground, and the reset button, which or the reset pin, which we're going to leave alone because we want it to be the reset button. You've got a total of 5 I/O lines. They can be inputs or they can be outputs. On this one, they're all grouped together into a single register or a single port called port B. Parts with bigger pin counts will have like a port A and a port D and a port E, and some of the high pin count ones are E, F, G, and groups of 8. Every 8 bits they come up with a new port. Now, so that's how we turn on the LED is we write a 1 to one of the bits in one of the I/O ports. But let's talk about port B because that's all there is to talk about on this chip. It's actually controlled through 3 different registers, and if you're going to do bit level stuff, which you almost don't have a choice with a project of this scale, you need to understand how port B works, and all the other ports work exactly the same way. They use the same architecture. There's 3 registers, port B, pin B, and DDRB, or data direction register for port B. Port B is the output port, pin B is the input port, and DDRB is the port that lets you assign whether each bit is an input or an output. And I go over each one of those. Data direction register B, a 1 in any of the bit positions makes the I/O pin an output. A 0 makes it an input, and you can change it. It's not permanent. If you need it to be an output right now and forever, you set it at the beginning and you leave it. If you need to change it back from an input and an output, you can under program control. It's just a bit in a register. If you forget to set, let me start over. When the chip first powers on, they're all inputs. So if you want to flash an LED, you need to take the bit that you're interested in and turn it into an output. You have to do that. That's the only requirement for initialization. When port B is your output port, if it's configured as an output, you write a 1 to it, that raises that voltage to a high level. I don't know if that's obvious to some people, it's not obvious to everybody. That takes it to, if you're running on 5 volts, it takes it to 5 volts. That's enough to turn on an LED. If it's, write a 0 to it, it takes it to ground. If you've wired your LED up backwards and the other leg is hooked up to 5 volts, and then you take the voltage down to ground, then current can flow. And that turns your LED on. So it depends on what you've hooked up to the output. It can sync or source up to about 40 milliamps. Then pin B, if you want to read a digital input, you have to read it from the pin B register. If you just read port B, all you're going to read back is the last value you wrote to the output register. It's not a true reflection of what's on that pin. If you're reading an input like a bump switch or something like that, you need to read from pin B. Also, if you write a 1 to pin B, that toggles the state of the I/O line, which is just a weird little thing they threw in for free, because you can do that a lot faster than reading and modifying and writing, and then reading and modifying and writing. You just do a write that toggles. So sometimes you
If
need
it's
to...
an output, then it'll flip it from high to low, low to high?
Yes, it changes the output state. Yes,
Wow.
the toggle function, which is pretty nice. Also, output port B, if it's an input pin and you write to port B and set a 1 to it, it enables a pull-up, an active pull-up on that line, which saves you having to put a resistor on the output. You know, saves you a penny. Or
It's in the 10 to 20K range.
well, it's not even linear. It's like closer to 100K. It's fairly
It's
high
like part, I've seen lower, but
on the AVRs.
some of them.
Well, it's a
20K maybe.
It's
200.
a MOS transistor. It's
Right,
not
so
a resistor.
it's not anything
It's-
precision.
It's not linear, and it changes over voltage and temperature, and they don't spec what that. It just pulls it up. So it's a weak pull up.
But it'd still be useful for like a button.
It is
That's
useful.
exactly
You
what
have a
it's
button
for.
connected to the ground
Yeah,
and all
button
you have is
connected to the ground, and normally that wouldn't tell you anything.
Right.
Okay, because there's no known state when the button is not pushed. And so if it's pulled up high, it's always high until you push the button. So it goes from high to low, high to low. Only when you push the button, otherwise it's floating, and you don't want that. So all that's built in.
And if you're spending any time switching back from input to output, realize that whatever you wrote the last time to the output will either leave that built-in pull-up enabled or disabled.
Yes.
So you kind of need to, if you're going to do any kind of switching, you have to pay
Yeah, if
attention.
you're doing some real fun multiplexing and stuff, and we'll get into a little bit of that. We'll talk about expanding what you can do with just this little chip. We will. So, yeah, where's all my color? I had a blue background. It was really pretty. And my font was different. That's it. That's the Blink LED program. Okay, you have a little include. And who's familiar with C? Who's not familiar with C? Okay, so you know what this is. And this is literally, that's the whole file. There's no other headers, there's no other libraries or anything like that you need. You include the AVR/IO H file, all these header files, which part descriptions, register addresses, all those definitions are installed when you install the tool chain. Then you just have one function, it's called main. You set up you declare an integer counter that we're going to use as a delay, otherwise it's going to blink really fast. You're not going to be able to tell that it's blinking. Then you do an assignment, and that's this line right here where I have DDRB equals 0.0 or 0x01, hexadecimal 1. That is just, now who's familiar with hex numbers and bits and bytes and the positions? Okay, I don't have to go over all that math stuff. That just turns on one bit in DDRB, so only PB0, bit 0 in that register is an output. All the rest are still inputs. And then we go into a while loop that goes forever, because while 1 is 1, it's going to do that. While 1 is not equal to 0, it's going to do that. Port B equals 1, that turns PB high. And then a for loop that just counts down from 30,000. And then port B equals 0. And then another loop. And so high, low, high, low. You hook an LED up to it, blinks on, blinks on, blinks on. Who can think of another way of toggling that output rather than writing a 1 and then writing a 0?
Write a 1 repeatedly to it, so it's possible.
To what?
Pin B.
But yes, yeah, it's tied to pin B function, because normally you would never write to pin B, so they found a use for it, you know, on that side of it. So, you know, without adding another register, here's the toggle register, because if you look at the register map, it's packed. They've already run out of room on some of the parts as far as where new
So you
peripherals
could
and
cut that
stuff.
down to a 2-line program to talk.
You
about
could, but it
PORTB.
wouldn't be obvious
Two
what
lines
it's doing.
while
loop.
You would be, yeah, well, two lines within the while loop.
Yeah.
It would be pin B equals
Yeah.
OXO1. And that would actually handle the toggling instead of having defined values. But for educational purposes, say what you mean what you say. It's very clear, nothing clever, nothing tricky.
Yeah,
But yeah, but you could do that
You
and
still
it
got
would
plenty of
execute
flash
faster.
left.
I'm sorry?
Still got plenty of flash in your 1K left for
You
this.
still, yeah, you would conserve that precious, precious memory, because believe me, I've run out many times on many projects, and when you know, you can tell, oh, compiler, optimize my code more, you know, squeeze it down. You can only squeeze, you know, so much, you know, 10 pounds of code into a 5-pound bag, you know, I mean, you can only put so much in there. And then return, this never happens. If you don't put it in there, it'll complain. And if you'll notice, the return type of the function main is int, because as it was for our fathers, as it was for their fathers before them.
Our forefathers, yes.
The main function returned to the operating system a status value of your application. Well, this is not an application per se, and there is no operating system. This doesn't go any. Literally, when you return, if you fell out at the end of main, or you did return, like it said there, which it won't because it's got a while loop that never ends, it would actually just go into a little loop that jumps back